good morning, everyone. I think I missed Cheng Rui, You Yu, Yu Jie, Tim, Huai Zhi, Jimmy, Guan Yu, Amelia, Doris, Yu Xiu, and Hui Xing. Good morning. All right, so the announcements this week. Similarly, you see the lecture. Hi, Wei Xiang and Liang Xin. The Calling Google Meet Sessions link and the assignments due includes PA number 5, quiz 19 to 21. Okay. And you know what? We'll start from quiz 19, which we talked about already last week, right? Before the exam. Yeah, I know to some of you it might be a little bit traumatic, but just hanging there, okay? It's okay, Wei Xiang. And this is quiz 19, the Lord of the Ring, right? So the people in the Helm's Deep needs to send a messenger to call for help from Gondor. But the messenger need to cross the White Mountain, which is full of orcs. Okay, so you're asked, pretend that you're Gandalf the Wise. How are you going to make sure that Gondor gets the message so that the Helm's Deep knows that there will be rescue coming, right? And you know what? I've already seen 2 teams addressing the quiz. Okay, so let's talk about what these 2 teams have, and then the rest of you guys can definitely think about your own solution. And for this quiz, the most unique, the better. Okay, so if you want to get a yellow mark for this quiz, come up with something that Team 1 and Team 15 did not come up with. Let's see what Team 1 says. Try to use animals with a message. For example, birds or mouse. Okay, and try to send a bunch of birds and mouse. So oh, very interesting. So flying. So it's orcs don't fly, right? The birds will be safe. And in case one bird gets shut down, how about sending a bunch of birds, a bunch of mice? So add some redundancy, then the likelihood of any of the bird or a mouse getting to Gondor will be much higher. All right, so that's Team 1 solution. Team 15 is very interesting. Maybe there are some secret paths which are only known by the locals. Mm-hmm. So while orcs are invaders and have no idea about them, then send some scouts, okay, with local guides, so that you can travel through the paths and then take back the confirmation from Gondor. Okay. So yeah, I know, because in the Lord of the Rings, we have creatures like this, right? Schmeagol's. He seems to know all the secret paths everywhere. Oh, wait, okay. Wei Xiang here, representing Team 5, also type up something. Helm's Deep can build underpass. Oh, interesting. So dig tunnels, okay? Like the dwarves do, okay? Or maybe get dwarves to help, right? Good, so dig tunnels to send a message. I see some of more of you coming, Catfish, Ziwei, and Justin. Okay, welcome. And we're now working on quiz 19. So hey, let's spend some maybe 5 minutes. 5 to 10 minutes. Let's see how the other teams come up with solutions. So now try to not use animals and try not to find secret passages, or try not to dig tunnels and send messengers underneath White Mountain. All right, so there are two more teams coming up with solutions. So Yun Tong, representing team 3, is saying that how about fireworks? If we could shoot fireworks high up in the sky and higher than the Y mountain, the Gondor people will see it, right? We don't have to send messages. Okay, so wireless transmission in a way, because it's exploiting the EM waves, isn't it? All right, visible light in a way. Yeah, I think that's also what people do, right? If they want to draw attention from people in the mountainous area, which is to do what? Smoke. Set fire and then generate smokes. And team 6 here, negotiate with the orcs. Okay, so this is a very brave solution, okay? So you might want to find a good place to negotiate to prevent the negotiators being eaten by the orcs. Okay, good. Well, I think you guys get the ideas. Okay, so in human history or even in the Middle Earth fantasy, there's always need to communicate, always need to send messages. Okay, and it happens also that the messages don't only get corrupted, like in RDT 2 something, what we're addressing is that if there's a bit error in a message, right? If you have a corrupted message. But you know what? The message can be lost entirely, much like the messengers passing through the Y mountains. Okay, so how do you make sure that the message gets through? And how do you make sure that helps the people should stay, or instead of fleeing, okay, the site? So that is what the RDT 3.0 here is trying to address. So this is the next generation of RDT. So in addition to addressing bit errors, RDT 3.0 also tries to address that a message can be just dropped entirely. Okay, so let's hear out why we need RDT 3.0 and what is the principle, okay, of recovering from a lost packet in RDT 3.0.
Now, the last version of RDT, the RDT 3.0. In version 3, we're going to make it very general. So there could be bit errors in the data packet in the acknowledgement packets, but there could also be losses of the data packets or the acknowledgement packets. So the new assumption here is very general. The underlying channel might have bit errors, but it might also have packet losses, both at the data side as well as the ACK side. Now, all these mechanisms we have in version 2, checksum, X, retransmission, and the sequence numbers to avoid duplicates will help, but only help for, bit errors. So, in case of packet losses, not enough. So we need to add extra mechanisms. And the extra mechanism is this. The sender waits for some amount of time for the ACK to come back. If the ACK does not come back within the time window, then retransmit the packet. Okay, so retransmit the data packet if no ACK comes back within that timeout interval. All right, so what we're doing here is to require setting of a countdown timer per data packet being sent. Okay, so when the data being sent, timer gets started. That timer is going to tick. If ACK comes in before the timer expires, cancel the timer. If there's no ACK coming in and the timer expires, retransmit the data packet. Right? So that's pretty much all to address the packet loss issue. Now, hey, some of you might be wondering, what should be the timeout interval there, right? Hey, internet delay could be changing quite a lot over time. So these data packets can be just delayed, or the ACK packets coming back can just be delayed. So in case they are slightly longer than the timer that we have set up, then we will be retransmitting data unnecessarily. Yes, okay. Some of the retransmissions might be unnecessarily a duplicate. Just like when ACK is corrupted, the retransmission from the data sender in 2.1 is also unnecessary. But it's okay. We already have the mechanism right there, which is the sequence number. that's going to address the duplicate issue. So no worry, even though if we didn't set the timer quite right. It's just that there'll be a lot more unnecessary retransmission if the countdown timer is too short. All right, so hey, determining what is the duration for the countdown timer, that is also an art. We'll also see later in TCP how that is calculated, how that is estimated. All right, so yeah, sequence number is necessary again in RDT 3.0. The receiver needs to specify the sequence numbers for the X, just like the data side needs to specify the sequence numbers for the data packets. And this is RDT 3.0 sender. Well, the usual technique, yeah, let me draw a line. So we just focus on one side of it, you'll see that the other side is similar. So what do we have here? Starting from the initial state, yeah, get a call from above, generate the packet, starting from sequence number 0, and what? Wow, we have these timer stuff, right? Starting a timer. And this is the transition next. If everything is going smoothly, receiving an ACK, it's not corrupted, and it's indeed ACK for 0. Then what? Stop timer. Now, if things don't go all that well, and the timer expires, then retransmit the packet and start the timer again. Because, hey, we just sent the data again, then the timer needs to be refreshed. Now, what is a bit unusual is in this transition. So what is this transition in 2.2? Well, yeah, the packet coming back from the receiver, if it's corrupted, or if it's clear that it's a negative acknowledgement, previously what did we do? We retransmit packet, right? Like calling UDT send packet here. But we actually do what? Nothing this time. Would that work? If it's corrupted ACK or a negative acknowledgement, and we do nothing, would that work? You know what? Hey, there's this transition, right? Yeah, so sender here would just not work in case we get this explicit, signals from the receiver, something is wrong. But eventually the timer is gonna fire as well. So that packet is going to be retransmitted. It's just that, hey, with these situations, we're just going to wait. So we'll just always wait until timeout. How do you like that?
How do you like that? Well, let's go through a few examples, and you might see a little bit better which way you like. Okay, whether to wait until timeout always, even in the corrupted ACK or negative ACK case. So here are the first examples.
Now I'll let you ponder how you like RDT 3.0. In the meantime, let's move on and see a few examples of RDT 3.0 in action. So scenario number 1 here is the null loss scenario. So everything is going well. Data, ACK. So you see, packet 0 being sent, receiver here receive 0 and send back ACK 0. ACK arriving at the sender side, receive what? Move to the wait for call from above for packet 1 state. So send packet 1, ACK 1, send packet 0, ACK 0, and go on and on and on. So this is a very straightforward scenario. Now the second scenario where we begin to see packet loss. Packet 0 go, ACK 0 comes back. Packet 1 goes, but dropped. So what's going to happen here? The receiver is not going to receive anything. And the sender side has a timer, right? So that's going to tick, tick, tick until, timeout. Resend packet 1 and restart timer. So ACK 1 comes in. Hey, there's a timer going on here, but because ACK comes in before the timer fires, so that timer gets canceled. So packet 0 go, ACK 0 comes back. So this is the single packet loss scenario. And the third scenario is the ACK loss case. So packet 0 gets out, ACK 0 comes back, packet 1 goes, and ACK 1 get lost. What's going to happen there is the timer for packet 1 is going to tick and tick and tick until what? Expiration. So this is going to trigger packet 1 being resent, and finally ACK 1 gets received, and data 0 being out again. Now what's a bit unusual here in scenario 3 versus 2 is that, packet 1 was actually received already. But it's received again because the ACK was the one being lost. Okay? Don't worry, because this is packet 1 and this is packet 1. For 2 consecutive packets carrying the same sequence number, receiver will not extract data and pass it further on. Receiver just send the ACK back again, okay? And that's going to clear packet 1, and therefore packet 0 can go on further. Scenario number 4 is to illustrate this case, premature timeout. So that is when the timeout interval is this long, but the ACK and data takes a long time to take a round trip back. Right? The scenario goes like this. Packet 0 goes, ACK 0 back. Packet 1 goes, ACK 1, takes longer than usual to come back. So at this time point, timer expires, and packet 1 here gets retransmitted. So packet 1 gets retransmitted before ACK 1 can come back here. Right? So when packet 1 gets retransmitted, timer for packet 1 is restarted. But the good thing is, hey, ACK 1 actually just, arrived. So from the sender's point of view, what's going to happen there is sender thought, ooh, ACK for the packet I just sent has arrived, so cool. Cancel the timer and send the next packet. So packet 0 goes. And that's going to trigger ACK 0 and come back. And data 1 goes, ACK 1 comes back. Data 0 goes, ACK 0 comes back. All right. Well, I hope it's just that easy, because we are actually not yet talking about when packet 1 arrives at the receiver, what's going to happen? Well, receiving packet 1, and receiver there will see this is a duplicate because I just received packet 1, right? So this is duplicate. Ignore it. Don't pass it up to the application layer, but still generate the acknowledgement to ensure that the sender is notified. So ACK 1 will travel back. Now, sender here received ACK 1. That's right after packet 0 is sent. What does that mean? Well, the sender there receiving a corrupted ACK or an acknowledgement that's not quite in sequence number that's expected, then it's probably a negative acknowledgement. So corrupted acknowledgement, negative acknowledgement, that should trigger retransmission in version 2. But in RDT 3.0, what do we do there? We actually ignore it, right? So some of us are not very comfortable about just simply wait until the timer. But you see here, hey, this will actually not trigger any further packet being generated. You'll see an advantage in the next scenario, where if we run RDT 3.0 with quick retransmission when there's ACK corruption or negative acknowledgement. So you see here, delay ACK, timeout expires first, packet 1 goes first. And ACK 1 there generates packet 0 to go, and so on and so forth. Okay? So this generates ACK 1 to send. But if, we're not running RDT 3.0, but an RDT 3.0 with what? Retransmission upon corrupted ACK or a negative ACK, then we send what? Packet 0. Okay, again. Because obviously packet 0 is corrupted, therefore we get ACK 1. So retransmit packet 0. And that's going to trigger another ACK 0. You see, packet 1, packet 1. ACK 1, ACK 1. Packet 0, packet 0. ACK 0, ACK 0. So for every data packet, for every ACK packet, there's going to be what? A parallel sending, duplicate of it. Is that good? Even though we try to retransmit early. Not that good either, right? Comparing this case and the previous case. So a trade-off.
So there's a trade-off in between response time and the bandwidth consumption. Okay, if you want it fast, you ended up sending 2 copies of packets and ACKs. But if you can wait, it's just 1 copy. So from RDT 3.0, you might see a little bit that there's no one solution being perfect usually in engineering. It's more often trade-off, and it really depends on what kind of quality of service you're looking for. Is bandwidth more scarce resource, or delay a more scarce resource? Okay, and that takes us to quiz 20. This is the second quiz today, and this quiz is to exercise you the finite state machines of RDT 3.0. And from here, you also see, because in the videos, you only see the sender side of RDT 3.0. Some of you might be thinking, hey, what about the receiver side? You know what? RDT 3.0's receiver side is identical to RDT 2.2's. Okay, so the receiver side of RDT 2.2 doesn't need to be changed, okay, in order to address packet loss scenarios. So what I'm showing on quiz 20 is on one side, RDT 3.0's sender, and the other, the receiver. Okay, good. And you're now asked to show the finite state machine transition sequence, okay, in the scenario. Send one packet, but the packet is lost. And then there's no more losses or bit errors afterwards. Okay, now tell me, and definitely go to Slack, WA quiz 20. Okay, write down the sequence of transitions that are triggered. Okay, and of course, for the sender and receiver, we start from the initial state. Okay, those are the states where you have the dotted arrows pointing to. All right, so let's see, maybe 5 to 10 minutes again. Okay, now let's work on this quiz. Wow, Guan Yu was really fast. Oh, I see Jia Hong. Oh, wow, okay, so hey, it does look to me that this quiz only need like 2 minutes. You know what? You guys are very good at it. I guess after you sing enough of these finite state machines and a few more examples, it doesn't seem all that hard. It's something that's not that you see every day, but you see that it's very straightforward. It might look complicated, but the operation of the finite state machines are very straightforward. In fact, how computers operate are exactly like this. Okay, the finite state machines in the early 19th century are called also the Turing machine, except that there's no the tape part. Okay, the data storage part. Okay, so this is a very typical way finite state machines to represent how a well-designed process. All right, so very good, because Polly also worked on it for a little bit, because Polly has not been working on the quizzes for a while. Yes, I also have T1 and then T3, T11 and T4. Okay, and that's illustrated, okay, in the PowerPoint slides with animation here. So first of all, first of all, we have the sender starting from the initial state, right? And sending a packet is triggering T1. And so a packet will be generated and sent, and a timer will be also triggered, right, and ticking. But this packet is going to be lost. Poof. So, hey, receiver will not be receiving anything, right? So T11, T14, none of these will be triggered. And what will be triggered next? Yeah, because there's a timer started here in transition T1. Therefore, next is to trigger T3. Okay? A timeout event occurs, and the packet gets resent, and the timer gets restarted. Okay? And the reason that the timer needs to be restarted is, in this scenario, of course, the packet gets through, but it's possible that the retransmission might not get through. Okay? So finally, packet goes through. No more bit error, no more loss. Therefore, we trigger T11, and therefore the receiver would go from the initial state to the wait for one from below state, right? And this acknowledgement will be sent back to the sender and triggering T4, okay? And at this point, we simply stop timer, and the sender moves to the wait for call one from above state. Good. I guess these finite state machines and how they work are very clear to you guys now. And we are comfortable to move on. Okay. RDT 3.0, you see that it's a complete mechanism that addresses bit error, okay, corrupted packet scenarios, as well as packet loss scenarios. Okay, you could have packet loss consecutively, no problem. Okay, RDT 3.0 is going to address all these possible problems. But okay, there are some other issues with RDT 3.0. You see that a working program, it's fulfilling and you might get grades after turning that in. But a working program might not be accepted by the public because of this performance issue. Let's check out what is the performance issue in RDT 3.0.
RDT 3.0. We spent quite a lot of time talking about it, and finally it seems to be working for the bit error case and the packet loss case. And you know what? It works indeed, okay, but it does not work that well. Okay? Let me use this example here to explain. So let's suppose we have a pair of sender and receiver. In between them there is this link, 1 gigabits per second. Okay? And the propagation delay one way is 15 milliseconds. And between the sender and receiver, the packet size is 8,000 bits. And that is the equivalent of 1 kilobyte. So this is very typical of a TCP connection's packet size. And you see also earlier doing the trace routes, 15 milliseconds is very typical between two routers on a local area network. And 1 gigabits per second link, this is very commonly seen. Some of the Ethernet connections are actually 10 gigabits per second already. Now, let's try to calculate. First, the transmission time. Well, you learned already in chapter 2, right? It's the packet size divided by the transmission rate. So packet size, transmission rate, 1 gigabits per second. And we get 8 microseconds as the transmission time. Now, the performance we'll be looking at here is this, the utilization of the link between the sender and receiver. Okay. If this is high, that means, ooh, sender is actively sending all the time. So usually the throughput is going to be better. But if the utilization is low, the throughput is not going to get any better. All right. Now, in order to calculate the utilization, let's recall how RDT 3.0 works. We send from the sender one data packet, and the sender there stop and wait for data to travel to the receiver. Receiver sends back an ACK, and ACK travel the network again back to the sender. And that's when the sender can decide whether to send another data. So sender there again, stop and wait until data travel through the network, ACK travel through the network, and then send another one. So you see that the sender there is working in cycles. Stop and wait, stop and wait, stop and wait. And each cycle, it's using this much amount of time to transmit actual bits, and this amount of time, so plus the round trip wait entirely for the entire cycle. So this is 0.008 millisecond, and this part, sending the packet and then wait, one wait and another wait. And here I'm ignoring the ACK packet transmission time because ACK packet is usually just very small. Okay, so that's one round trip time plus packet transmission time, 30.008 millisecond. The overall utilization on this link is very, very low, 0.00027. too many zeros. And if I illustrate the scenario I just described there, sender, receiver, and this is timeline. Okay, at time 0, first packet bit is transmitted. So right here, first bit goes onto the link, and it takes this amount of time. That is the time to transmit all bits on the packet. So last packet bit transmitted is right at this time. Okay, that is the packet transmission time, L divided by R. And these bits is going to travel halfway to the receiver and another halfway back to the sender. So first packet bit arrives right here. This is what? The propagation delay. Okay? And this is also propagation delay. So 2 propagation delay plus L divided by R. This is 1 cycle. Within a cycle, only this amount of time sender is being active. Okay, only this amount of data is being transmitted. While the entire duration, right, the sender can just keep pushing bits out, okay, onto the network interface. So you see again, the network utilization, L divided by R over the entire term, RTT plus L divided by R. Very low utilization. And that low utilization can be translated here. The throughput on the 1 gigabit link is only 270 kilobits per second. This is not even enough to send any video that would be sensible. So you see here, RDT 3.0, the design itself, although it works, but it limits the use of the physical resources. Okay, we're only sending 1 packet and then stop and wait until we can send another one. Now that I show this plot, then you know, yeah, obviously to increase the utilization is to send multiple packets per round. Indeed. So let's look at the plot in a bit more detail, just like we did in the previous slide. So sender, receiver, and timeline again. So this is the time we send the first packet, the end of the first packet. This is the time, first bit arriving at the receiver, last bit arriving at the receiver. At this point, the receiver can send back acknowledgement. So this is the time the acknowledgement arrives at the sender. This is the sender can begin sending the next round of packets. So how long is a round this time? Well, this is one-way delay, right? This is also one-way delay. So round trip delay plus L divided by R. So the same. In each cycle, we now send multiple copies of packets. So now we're sending 3, so 3L divided by R, right? So utilization is now 3 times higher than the stop and wait scenario.
All right, so isn't that nice? The pipelined RDT. So in fact, it's a different class of RDTs. Okay, you see that it's going to be more efficient than the RDT 3.0. And in that class, there are actually not just one protocol one could come up with, not just one RDT we can come up with, there are actually 2. Here's the overview of the pipelined protocols.
And this takes us to this new class of RDTs called the pipelined protocols. Okay. What it said is, let me repeat myself, the sender allows multiple packets being sent per round, okay, or multiple packets in flight. By in-flight, I meant that these are just data packets going out. They are not yet acknowledged. So it's illustrated better here. So this one on the left is stop and wait. This one on the right is the pipelined RDT. So we see multiple data packets go, not yet acknowledged, and their acknowledgements will come back in a sequence, okay, in a round to the sender. Okay, so a range of sequence number needs to be increased. So previously in RDT 3.0, we used just 1 bit, right, 0 or 1. But now we need to allow multiple packets going out simultaneously. And we need to make sure that we acknowledge each of these packets. So we need to tell each of these packets in flight apart. The sequence number definitely needs to be expanded. And we'll need buffering at the sender and the receiver side as well. Because, hey, what if multiple of these packets in flight are dropped? They need to be retransmitted again. So buffer definitely at the sender side is required to store those packets that are not yet acknowledged. Receiver here will also need buffer space because hey, when this packet is lost and there's other packet coming in subsequently, should we keep them or should we drop them and have the sender retransmit again? And what about these other packets that has already arrived? Okay, so there's some buffer space also, okay, needed in order to address different needs of different designs. So buffering required, a longer range of sequence numbers required. Okay. Now, in the next few slides, what we're going to introduce are just two different flavors of these pipeline protocols. So they are the big categories. First is the go back end. The second is selective repeat. Now, one can, of course, further tune the go back end so that it works slightly differently. Hopefully, the second version works slightly better than the fundamental version. Similarly for the selective repeat protocols. Okay, so here's the overview slide that contrasts two big categories of pipeline protocols. On the left, the go back end. On the right, selective repeat. Right? They are the same this way. Both of them allow having multiple packets in flight, in a round. Okay? Well, that's the basic ideas of pipeline protocols. They must be the same this way. And then everything else will be different. First of all, okay, what the sequence number in the ACK packet means, very different. One is to indicate I'm acknowledging an individual packet. So when the receiver in selective repeat sends an acknowledgement, that sequence number in the acknowledgement is to acknowledge exactly the data packet carrying that sequence number. But for go back end, the receiver sends back acknowledgements, but the acknowledgement carries a sequence number such that all the data packets before that sequence numbers are acknowledged. So this is a bit odd. Okay, so that one sequence number seems to be acknowledged all the packets before that. But the fact is that what the receiver is doing is this. The receiver will not add packets if it arrives and the receiver finds that there's a gap in between. So packet 1, 2, 3 missing, 4. Okay. When 4 arrives, the receiver does not send back acknowledgement 4. Instead, it sends acknowledgement 2 because there's a gap in the middle. So what the receiver of go back end here is saying is, I'm actually telling you to which point I do have consecutive receive data packets. So the next one is, the beginning of a gap, definitely. And the two categories work also very differently here. Timer. Okay, if you recall in RDT 3.0, we need a timer in order to tell whether a packet is dropped or not. Yes, go back end and selective repeat, both of them implements timer. Okay? But in selective repeat, there's one timer for each packet that is still in flight, not yet acknowledged. Okay, so one timer, one packet. But for go back end, there's only one timer for the oldest unacked packet. So in one round, there'll be a lot of packets being sent, multiple packets being transmitted. Okay, there's going to be just one timer for the oldest unacked, meaning if you send one flight out, there's just going to be one timer for the first one in that flight. Okay. And if the first one is acknowledged, there'll be a timer for the second packet, that is now the new oldest packet that's not yet active. Okay. So, one timer for a flight of packet in go back end. And the last difference is this. Okay. For selective repeat, when timer expires, the sender only retransmit the unacked packet. So whatever that timer says, if this is for sequence number 10, then it only retransmits packet 10. But in go back end, when the timer expires, it's going to retransmit from that oldest unacked packet. So all the unacked packets from the oldest one to the newest one. All right, so each timer is going to trigger retransmission of the rest of the flight of the packets.
All right, so that was the two categories in pipeline protocols. We'll talk about go back end in more detail in the next hour, and it's probably better that we take a break now. So let's take break. It's 11:05. Let's resume the lecture 11:15. And in the meantime, if you just wake up and join us, quiz 19 and 20, find your teammate and try and see if you can finish these quizzes so you don't have to work on them during the weekend. All right, now break. so we had a question, and there's one more very interesting answer for quiz 19, right? Being Gandalf, what can you do to make sure that you get help? So Team 4, Amelia was saying, hey, Gandalf can cast a very bright light. Okay. Well, and hey, Team 4, look it up from Google. Okay. So what they would do is they cast the very, very bright light and blind all the orcs. Okay. So it'd be a chaos. And then the messengers can sneak through White Mountain. Cool. It's a little bit cruel. Okay. It's a little bit cruel, but seem very effective. Okay. It's a little bit scary. And there was a question, I think, from Wei Xiang. So Wei Xiang was saying in selective repeat case, okay, when the senders are sending multiple packets and many packets, however, during the same time, it might get an ACK for some of the earlier packets. Okay, does the sender receive and send packets at the same time? You know what? It does. Okay, it does. Sending and receiving will be working on concurrently. Okay, will be going concurrently. But you see that I use this term concurrent because it's not exactly parallel. Okay, as you are sending, you also receive. Okay, it's more this. Okay, because the time it takes to receive a packet or to send a packet usually very short. Okay, and if you interleave sending of the packets and receiving of the packets somehow, okay, then it will feel like you are doing this at the same time. Okay, so the sender there might be, you will feel like the sender is receiving and sending packet at the same time. And this is exactly how the process is running on modern day operating systems make you feel. Okay, because for example, Poly is running OBS and Slack and Google Me and all these processes seemingly at the same time. But there's usually just one process running on one of the CPUs, one of the threads on my CPU. Okay, so you have multiple processes seemingly at the same time. All right, so now let's start. Go back in, and you know what? Pay attention because the last quiz for this week is coming right after the overview video. And you know what? Polly is very happy that after the first exam results are released, you guys still have the energy, okay, and brave enough to continue paying attention to the lectures. This is great. But I do notice that some of you wake up a little bit late. Okay, now the first video of Go Back In.
Let's look closer into the first categories of the pipelined RDT, the go back in. So this is just the sender side, and we'll come to the receiver side in a couple slides. And first thing first, the packet sequence number in go back in. If you recall in RDT 3.0, we only allow one data packet goes in out without being acknowledged, isn't it? And in that case, we just need one bit sequence number to tell the old packet and the new packets apart. But now go back in being a pipelined RDT, which we allow multiple packets being out in transit without being acknowledged. So your intuition should also tell you that, hey, you need a higher number of sequence numbers to tell all these in-flight packets apart. You are correct, and we now definitely need more, and k here is obviously larger than 1. Okay. Now, having k bits in the packet header, okay, as the sequence number field, then you see the sequence number can range from 0 all the way to 2 to the power of k, subtracting 1. Next, in go back in, or generally the pipelined RDT, we do have this thing called the sending window. And the sending window is usually associated with the limit, okay, we call the n, or the sending window size. Okay, so n here is to limit the number of unacked packets allowed. And go back in, this is the number of consecutive unacked packets allowed. It's also illustrated here. Okay. From the first packet in flight to the last packet in flight, the max range is n. Right? So At any given point in time, we allow only up to n packets being in transit, not yet acknowledged. And so you see here, this thing is also called the sending window, right? And n here is the sending window size. Now let's take a closer look at the plot over here. So each of these slim rectangles are packets. So the green packets are the very early packets that are already sent and already acknowledged. So this is in the middle of the sender transmission, as you see. And yellow packet, starting from here, the send base. So this is the first packet that is being sent out and not yet acknowledged. And there will be a number of these. So yellow ones are the packets already generated and sent, but not yet acknowledged. Now, depending on the application level source, the message could be large or small. Okay, so this is illustrating a case when the message is not that large, meaning you don't need to generate that many segments at the transport layer to cover the entire message. So potentially, within the limit n, we might have some sequence numbers that allow us to generate packets to send out, but we don't really need them. So the blue ones are usable, but not yet sent. Okay, so essentially, yellow plus the blue ones should be less than n. Right? Now, to indicate the beginning of the usable packet sequence number, we use yet another variable, the next seek number. Right? So send base, or sometimes I just call it the base, okay, is the base of the sending window. Next seek number is the next available sequence number that we can generate data packet within the window n. Right? And the last one, so these blank ones are simply outside of the window limit, so not usable. Right? And here, let's assume, okay, send base here finally receive an acknowledgement, and it's acknowledged, so we turn this into green. What do we do here? Now this one is green, isn't it? So send base is only to indicate the first unACK packet, so we actually need to what? Change it to this packet sequence number. As a result, we shift the window, and it's beginning from here, and include the next blank packet and turn it what? Blue. So the window is actually sliding over by one packet. So such a window is also called the sliding window mechanism. So when acknowledgement packet is received, you see these yellow packets turning green gradually, okay, and the window sizes is sliding over and then casting more blank packets into blue ones. All right. Just to make sure that it's clear, send base is the variable in go back and sender that always points to the base of the sending window, which means it's always the first yellow packet's sequence number. So the send base will only be changed when the first yellow packet is acknowledged and turned into green. So send base can no longer be pointing to a green packet, and as a result, it needs to be moved to the sequence number of the first yellow packet now. And you see window then here is sliding over by one. The next seek num is always pointing to the next sequence number in case we need to generate a new data packet. So in this scenario, it's pointing, of course, to the first blue packet that is useful and not yet sent. So because when we get a call from above and we need to generate a data packet, then we'll turn this blue one into yellow. And the next seek num is going to be shifted over and reassigned to the first blue packet after sending. And we do not shift the window size at all because the send base is not changed, and the n here is a constant. But be careful though. There'll be scenarios where, hey, all these blue ones are actually yellow, meaning, yeah, the sender does have large message to send, and we are actually exhausting the entire window size to send the message already. In that case, the next seek num will be pointing here at a blank packet. Okay, that is the next available sequence number to generate a data packet. But it's not quite yet pointing at the blue one because, yeah, there's no blue packet at all. All right, so next seek num, to be very precise, it's just to point into the first sequence number in case we need to generate another data packet. The rest of the go backend you heard a little bit already about. The ACK, the sender received, is going to be a cumulative ACK. Okay? What it means is that in the sequence number of the cumulative ACK, it indicates all the data packets before this number n are acknowledged. Okay, so all packets before n, including n, are green. Right? Now, if the sender receives duplicate acknowledgements, so hey, ACK n has already been received, but the next moment, another ACK n is received. What does that say? If you recall earlier, yeah, that usually meant, oh, packet n+1, there is a gap at the receiver. And receiver does not send acknowledgement up to sequence number n if there is actually any gap before it. Right? So receiving of a duplicate ACK at sender side indicates, yeah, whatever n is +1 is a packet that's missing. Timer. Yeah, there is only one timer for an entire flight of an ACK packet. So it's a timer associated with the base, okay, of the in-flight ACK packet train. Okay, so that is essentially this. Yeah, the oldest in-flight ACK packet is always indicated by the send base. In a way, yeah, there's a timer associated with the send base, essentially. Whenever the send base is changed or whenever the send base is refreshed, we refresh the timer or restart the timer. If it's a bit unfortunate that we do have packet loss such that the timer needs to time out, then we retransmit the entire flight of packet, starting from n all the way to the highest number that's not yet ACK. So that means starting from the send base all the way to the last of the yellow packet. So timeout indicates the entire flight of the yellow packets will be retransmitted.
All right, so that was the basics of go backend. So let's exercise the notations Polly used in the intro slides. So you have the green packets and the yellow packets and the blue packets and the empty, or now I use gray color to indicate the empty slots. Okay, and let's assume this is a go backend sender. And currently, the first yellow packet is number 23, the sequence number being 23. The first blue packet, sequence number being 33. And the first gray packet is 39. Okay, so you know also that the send base will be 23. The next seek num will be 33. And the first gray packet sequence number is 39. Okay, so Q1 asks, okay, given the state of go backend sender, if suddenly the sender sends two more packets, okay, what will be the send base, next seek num, and the first gray packet values? Okay. Q2, again, given the GB go backend sender state right now, 23, 33, and 39. If suddenly the sender receives an ACK for packet 23, what will be the new send base, new next seek num, and the new first gray packet sequence number? Q3 is very similar to Q2. What if, okay, given the send base being 23, next seek num being 33, and first gray packet being 39, if we suddenly receive an ACK for 32? Oh, cool. That's actually what? Acknowledging to the last yellow packet. Hey, go backend is what? Cumulative ACK. So what do we do? What will be the send base? What will be the next seek num? And what will be the first gray packet if we get the ACK for 32? Okay. So tell me, in Q1's case, what is the send base, next seek, first gray packet? In Q2 scenario, what are these three values? Similarly, in Q3, the values of these three values. All right, so move on to Slack, WA Quiz 21 channel. You see that Polly posted also the slide there. And you know what? This might take a little bit time, so let's spend some 10 minutes here. How about that? Okay, so get it clear. Okay, so yeah, in previous year, I probably asked Q1, after sending 2 more packets, what would the send base, next seek num, and first grade packets will be like? Okay, and then continuing after sending 2 more packets, and then you receive an ACK for 23. What will be the new send base, next seek, and first grade packet will be like, and so on. But this year, or this semester, I asked to treat all Q1, Q2, Q3 independently, assuming that the prior state is what you saw on the left of the slide. So they are independent. Okay. So Q2 is asking, if the starting send base is 23, next seek num is 33, and the first grade packet is 39, and suddenly you receive an ACK for 23, what will be the 3 numbers values are? Okay. Very well done, Youyu. You paid attention. Wonderful. Angel from heaven. Yeah, sorry guys, because I don't want you guys to just, copy paste solutions from previous semesters. Because that way, you're just memorizing things. Very good. Doris? Sorry to trick you guys, but you see that if you think about it, you know very well as well that you want to exercise these on the spot right here. Okay, instead of backward engineering, right? Given the solutions being this, then this must be happening this way. So I mean, we all do hacking. For programming assignments, you need to do that. Okay, that is encouraged. Okay, given that this is the expected behavior of your program, what is missing in your code? But a lot of times you want to also learn forward instead of backward. Okay, learning and hearing people or description of the mechanism. Okay, what should be the right thing that's happening? All right. Yeah, so I kind of changed the way I describe the problem this semester. Okay, instead of treating Q1, Q2, Q3 as a scenario after another, they are independent. There we go. Very good. You've got it. There, Wei Xiang. I know you know. Oh, wonderful. I guess this is just typo, right, Liangxin? It's okay. Love. All right. So yes, you know now, right? When for Q1, so let me go to the quiz here. So you see that how all the teams, okay, have get the idea. And it's actually okay to make mistakes. Just that let's try to not make the same mistake, right? No worries about making mistakes. Okay, so it's actually an opportunity to learn, right? So you see that after sending 2 more packets, what does that mean? Oh, we need to take 2 more of these blue slots to send packets, right? But send base remain the same because it doesn't say that we receive an acknowledgement for packet 23 or 24 or 25. And window size is fixed, so number 29 for the first grade packet is still there. Okay, so unless the yellow move, unless the base send base move, otherwise the first grade packet won't move. Okay. So the difference between the first grade packet to the send base is always fixed, which is n. And in this example, it's 16. Okay. So once you know the send base, you know the first grade packet must be the send base plus 16. And number 33 here we need to change because we send 2 more packets. So we take 2 of the blue packets and we turn them yellow. So the send base, the next seek num is added by 2. That's why I see that you guys all have 35. While the send base remain the same. First grade remain the same. Second scenario, assuming the base is 23, 33, and 39. We receive an ACK for 23. So, cool. We get to turn the packet number 23 green. So the first yellow is what? 24. And hey, first grade is always send base plus 16. So every time you need to change send base, you change also first grade. Therefore, for Q3, we suddenly receive ACK for 32. So all the packets, including 32, turn green. So the first yellow is 33. But you see, in this case, 33 is blue as well. So there's no yellow packet, okay, in the window. Indeed. So send base, you thought that it's always the first yellow. Well, if there are no yellow, it's also the first blue. Well, sometimes it's also the first blue. Okay, so you see that first yellow 33, first gray 33 plus 16. Okay, and so 33, the first blue did not change. Okay, very good. So you guys have got the idea of the go back and window because it's cumulative. It's a little bit odd. Okay, and in RDT 3.0 and before, you have just stop and wait. There's no multiple packets in flight there waiting to be acknowledged. Now you do have many, right? All these yellow packets are waiting to be acknowledged. Okay, so this is to allow you to exercise to get this notion of pipeline sender, okay, and how it's going to operate in the pipeline sender. And this is particularly the go back end flavor. Okay, now let's move on. I think it's you guys have got it. And next are the finite state machines. Okay, let's start from the sender side. And I'll have to review RDT 2.2, 3.0 before we can talk about the go back end sender.
Go back end sender is finite state machine. Before we start talking about this, let me review RDT 3.0 sender's finite state machine. And here it is, the RDT 3.0 sender. Okay, so we're starting here. Okay, and there are 4 typical transitions: 1, 2, 3, and 4. So first is to get a call from above. We generate the packet starting from packet 0, send it out, and then start the timer. The other is getting a feedback from the receiver. If it's not corrupted and it is indeed the ACK we're expecting, then that's a positive acknowledgement, so we stop timer and move on to send the next packet. Third is when it's a little bit unfortunate, the packet is not correct or not arriving at the receiver, timeout will be triggered. So we retransmit the packet and start the timer again. Last one is when you get the feedback, it's unfortunately corrupted, then we do nothing. So we kind of ignore these 2 conditions on purpose. The second condition is, yeah, we get an ACK all right, but this is what? Carrying 1, which indicates this is a negative acknowledgement. So in these 2 cases, instead of quickly retransmit, we just ignore. So this is a quick refresh of RDT 3.0. In go back end sender finite state machine, we also have these 4 transitions. getting a call from above, receiving feedback from the receiver, and it's not corrupted. Having the timeout event, as well as getting feedback from the receiver, but it's corrupted. Okay, very similar. And then we go through them one by one. Now let's start from the getting a call from above transition here. Comparing to RDT 3.0's getting call from above transition, this one is pretty long. Yeah. And it starts from a if-else condition check. And the condition is this guy here. If the next seek num is less than base plus n, so base plus n is what? The window range, isn't it? If the next seek num is within the range, that means, okay, we can now generate still some data packets. So, makes sense. We go ahead and create the packet using the data from the application layer, generate the checksum for the data, and then give it the sequence number. Okay. Here. We are now using an array of send packet here to store all the packets being generated. This is because go backend is a pipelined RDT, meaning there will be multiple packets in flight, so they'll be generated, being transmitted, but not yet acknowledged. So these send packets will need to be stored temporarily at the sender before they are acknowledged, because chances high that you need to retransmit it somewhere later. Okay, so we need an array instead of just one packet there to store the packets that are in flight. Next step, send the packet out. Oh, and then we need to start the timer, right? This is to handle the cases we could have packet losses. Just like in RDT 3.0, the difference to RDT 2. something is to have these timers. So we need to start timer, definitely. But in go backend, we have one timer for the entire flight of ACK packets. So we need to check, right? We cannot be starting a timer for every data sent. So here we're checking. If the packet we are now generating is indeed the base, the first yellow packet, because the timer in go backend is associated with the first yellow packet, so associated with the base. So only when the packet we're generating is the base, then start timer. Otherwise, don't. So this ensures that we have only one timer for one flight of ACK packets. And the last is straightforward, just increment the sequence number by 1. So this is if the next seek num is within the window. Otherwise, refuse data. So this is telling the application layer process saying that, hey, I cannot be sending more data packets. So you hold on and you try calling the RDT send after some time. And the second one that we'll examine is this guy here. Right, so this is supposed to be the case where we receive acknowledgement. And it's a new one, therefore we could move on, right? So let's take a closer look at how the move on is like in go backend sender. First of all, the checking condition. Get a feedback packet coming from the receiver from the lower layer. And if it's not corrupted, good. So the feedback packet is not corrupted. So this must be one of those cumulative ACKs. So inside the ACK, there's going to be carrying a sequence number. So why don't we get that sequence number out? So get ACK num. Okay, so this is a new function call introduced into go backend's finite state machine. So that is just a bit abstract, but what it does is to get the sequence number in the cumulative ACK packet here. Right? And we simply change the base to that sequence number plus 1. Right? So this is the first packet that is unacked. Hey, makes sense, right? Receiver sends a cumulative ACK. So that ACK carries the sequence number n, which indicates all the sequence numbers before that, including n, are acknowledged. And the n plus 1 is the first in the gap in the receiver. The first one, that ACK cannot be acting. Okay? Therefore, base is assigned to that value. Okay, makes sense. Oh, but we check. So just like in the generating data part, there are a lot more check. Being careful here. If the base is not the next seek num, what does that mean? Base should be the first yellow, and next seek num should be the next data that is allowed to send. But next seek num cannot be a yellow packet, right? So if they are the same, that means there are no yellow packet at all in the window. Okay, which means all the packets that's not yet act at this point in time are already act. Okay? So stop timer because there's no pending packet, okay, waiting for acknowledgement. Otherwise, yeah, restart timer. So we receive a cumulative act. The base is reassigned such that it's pointing to the first yellow packet. And so we refresh the timer for the first yellow packet for the base. So restart timer. Right? So the only thing that's a bit odd is this. There's an if condition to check whether we should stop the timer because all standing packets are cleared. All yellow ones suddenly turn green. Or we need to refresh because the base is either refreshed or changed to a new value. And therefore, we need to restart the timer, okay, for the refreshed first yellow packet.
All right, so now the next two transitions in the sender.
And the third transition is straightforward. It's actually very similar to RDT 3.0's timeout event. Yeah, we restart the timer and retransmit the packets. In RDT 3.0 sender, we retransmit only one packet, but this time in go back in, we retransmit for the entire flight of packets starting from the base to the packet right before next seek none. And the fourth transition is this: when the sender received a feedback and it's a corrupted feedback, then we do nothing. So this is just like in RDT 3.0, when the sender receives a corrupted ACK or a duplicate ACK, which is a negative ACK, it does nothing. Okay. Now the difference here though is that it only handles the corrupted ACK case. What happened to the duplicate ACK? In go back and sender, yeah, it's actually handled here. When the sender receives an ACK, it's not corrupted. Whether it's a new ACK or a duplicate ACK, the actions are the same. If it's a new ACK, the base will shift to the right. But if it's a duplicate ACK, if it's a duplicate cumulative ACK, the base will remain the same. Right? Would this be a problem? Now, some of you might not be very comfortable with this, right? Because, hey, if the base remains the same, what do we do here? Yeah, we'll be definitely in this situation, right? Yeah, there's an unact packet somewhere and the base remains the same. We'll be restarting the timer, meaning the first time that base is receiving an ACK for all the packets before the base, the timer for that base has already been started. And now we're reassigning the base to the same value and restart the timer. That means we're extending the timer interval for that base. How do you like that? Think about it. And the last bit of the go back and sender, or shall I say the first bit of the go back and sender that we actually taught last, is the initialization of the sender. Okay, so the base, starting up the window, is initialized to sequence number 1. Next seek num is also initialized to sequence number 1. So this is unlike the RDT 3.0 sender receiver, always starting from packet sequence number 0. In go back and sender, textbook authors decide suddenly that they want to start from the sequence number 1.
All right, and last video about go back and finite state machine is the receiver end of the finite state machine, and it's surprisingly simple.
Now, the receiver finite state machine of go back in, it's actually quite simple. Let's just skip the initialization and focus on the two transitions possible. Among the two, this one is the more straightforward. We receive the data, get a call from below, and check the data, it's not corrupted, and check the sequence number of the data. Has seek num there is a function newly defined for go back in again. So what it does is simply checking the sequence number in the data and see if it matches the expected sequence number, which starts from sequence number 1. So if we receive packet 1 and it's expected, extract data out of packet 1, pass the data up to the application layer, generate ACK packet for packet sequence number 1, send the ACK out, increment the expected sequence number. Okay, so this is the simple case where everything works as expected. No error, no loss. And the second case is the default transition. What default meant is just all the other conditions that's not matching the previous transitions condition, which means the data can be corrupted or the data received not corrupted but not carrying the sequence number expected. So here, corrupted data or data packet that's not in the expected sequence number. Now this could be a duplicate data packet. This could also be a data packet carrying the future sequence number. So in either case, which means default is just to send the same packet again. That is the packet generated here, which is the add packet that is generated previously when data arriving correctly and in sequence. So in case of corrupted data, out of order data, we discard the data, no receiver buffering, so there's no extract of data, no passing of the data up to the application layer. And all we do is simply react to the data with the highest sequence number arriving correctly in order. So go back and receiver there. Works a bit odd, not that intuitive, but it's very simple. It always acknowledges to the data packet that is the highest in sequence number for all those who arrive correctly and in order. So all the receiver needs to track is the expected sequence number. And that's pretty much all. At the sender side, if a duplicate ACK is received, that is essentially saying either the data previously sent is corrupted or the data previously sent is lost.
All right, so now the final videos for today. Let's take a look at the go back and example. Well, it's a little bit complicated because of the nature that we have multiple packets in flight. So it's going to take a while. Okay, first part of the example.
Next is to walk through an example of go back in, following the finite state machines. So then we go back and recap. Go back and sender's finite state machine and the receiver finite state machine, just so that you can follow. And real quick, the sender side of go back in is this. If we get a call from above, we check real quick whether next sequence number is within the sending window, which is base plus n. If it is, then we generate packet and send it out. And then check whether we should be starting a timer. And the condition to start the timer is if this next seq number is indeed the base, and then increment the sequence number. All right, so check whether the next seq number is within the sending window. If so, generate the packet, send it out. Check whether we should start the timer. So next seq number, whether it equals the base, and then increment the next sequence number. If we do not pass the condition whether the next seq number is within the sending window, then ask the application layer process to wait. All right. Now, back to the example. Let's assume the window size is 4. And the sender's application layer process is sending data all the time. So sender here gets call from above all the time. So let's see. In the first call from above, right, the base and the next seq number are both initialized to 0. Now the first call from above is going to trigger checking whether the next seq number is within the sending window. Sending window starting from base and window size is 4. Next seq is initialized to 0. Is 0 less than 0 plus 4? Yes. So we generate the packet, send it out. And next to what? Check whether we need to start the timer. And the condition to start the timer is only when the next seq number equals the base. Next seq number is 0, base is 0. Cool. Packet 0 is indeed the first of the first flight. So start the timer here. And next is just to increment the next seq number to what? 1. So next sequence number here at the beginning is 0. Now increment it to 1. So if we get a call from above again, next seq number, is it less than base, still 0, plus 4? Yes. So generate packet 1. 1 here is the next seq number, isn't it? Send it out. Check whether we should start the timer. Next seq num is 1. Base is 0, not matching. So the second packet in flight does not start timer. All right, just increment the next seq num. So here, the third call from above will start from next seq num equal to base 0 and 4. Is 2 less than 0 plus 4? Yes. So we generate yet another packet. Next seek num equal 2, send it out. Do we start a timer? Next seek num equal 2, base 0, therefore not matching, not starting timer. Increment the sequence number to 3. Right? Is 3 less than 0 plus 4? Yes. Generate packet 3, send it out, not start the timer because next seek number is 3 and base is still 0. Right? And we increment the sequence number to 4. And now we get the fifth call from above. And that call from above will check, is 4 less than base 0 plus 4? It's no longer less, right? So what do? We go to the refuse data part of the if condition. So yeah, the application layer process is asked to wait, and sender will pause sending for now. And these packets will go out to the internet and hopefully reaching the receiver, while there's a timer that's ticking and ticking, ticking, and that is associated with the base, the packet 0. All right. And here's to quickly review the receiver go back in. If we get a call from below, the data is not corrupted and carrying the expected sequence number, simply extract data, pass to the application layer, generate the ACK, send the ACK, and increment the expected sequence number. And otherwise, just resend the ACK that has been generated previously. Now, the receiver. Okay, receiver here will be receiving packet 0. Yeah, it's not corrupted and it's expected, right? So expecting sequence number 0, receiving sequence number 0, therefore we send ACK, expected number 0. Next, yeah, we get a call again from below, packet 1, not corrupted, and it's in sequence, therefore we send ACK for the highest data number that has correctly arrived and arriving in order. So these are being sent back to the sender. But packet 2, oops, is lost somewhere on the internet. But packet 3 will arrive. It's not corrupted, but is it expected? We're actually expecting what? Sequence number 2. So we do not extract data. We actually trigger the default transition, if you recall, and just resend the ACK that is previously generated. So ACK 1 is being sent again. So right here. All right. And now we come back to the sender side. Okay, we'll be receiving ACK 0 here. All right. So receiving ACK 0. It triggers sender finite state machines. Oh, the transition at the bottom, isn't it? Receiving a call from below. Yeah, receiving a feedback packet from below. What do we do there? Yeah, let's recall and go back. Yeah, so here, quickly recall. Okay, this transition, getting a packet from the lower layer, and it's not corrupted. What do? Set the base to the sequence number in the ACK packet plus 1. And then we check whether we need to stop timer or refresh the timer. Now, only when the base and the next seek num are equal, then we stop timer, because the base here is empty, meaning no yellow packets at all, because next seek number is the first blue. So only when the base and the next seek number are the same. Otherwise, restart timer. Okay. Now we can come back here to examine. Yeah, what is the action the sender should be taking? Okay. First, receiving ACK 0. So that's triggering the transition at the bottom, a feedback coming from the lower layer, and it's not corrupted. So what we do is to extract the sequence number in the ACK, add it by 1, and that will be the new base. So base here is moved by 1 position. The next thing we do is to check whether the base equals the next seek num, right? If they are the same, that means we should stop the timer, because hey, all the data packets are already added, right? But otherwise, then we restart the timer. So hey, base is 1, next seek num was previously 4, isn't it? That's why we are waiting here. Okay, so we cannot be stopping the timer. Instead, we should what? Restart the timer. So this timer here, original ticking, will be canceled, and we restart the timer here. And that timer is going to be associated with the new base, which is 1 over here. All right. And then, hey, sender is trying to send data. So quickly get a call from above. So we trigger the top transition. So next seek num is 4. And 4, is it less than the base 1 plus the window size 4? So together 5. 4 less than 5. Cool. We can generate packet 4 and send it out. Is the sequence number base equaling the next seek num? No, so we do not start timer here. All right, so base is 1, so that means base, there's already a timer running. All right, next seek num, 4, not equaling 1, so not starting a timer here for generating packet 4. So timer is still associated with the base 1. All right, and then we increment the sequence number by 1, so 5 here. Similarly, receiving at 1, we set the base to 1 plus 1. So the base is now what? 2. Is the base identical with the next seek num, which is 5? No, therefore we do not stop timer, but instead we restart timer. So t removed there, and t is restarted with the new base, that is 2 over here. Okay, so t for 2. So this is t for 1, and this is t for 0. And at this point, one slot open up, getting call from above. Yeah, 5 is less than 2 plus 4, 6. Therefore, we generate packet 5 and send it out. And do we start the timer? No, right? And increment the sequence number to 6. And yeah, another ACK 1 is coming in. Okay, this is triggered by receiving packet 3 without packet 2. So ACK 1 comes in, triggering the bottom transition, not corrupted, set the base to 1 plus 1, 2. Well, that is the same, right? Base and next seek number, still not matching, therefore we restart timer. Ooh, so hey, we actually killed the old timer for base 2. Now, restart timer for base 2. That means, wow, this base is actually, waiting a longer time to expire to retransmit. But it's okay. It will still work. Just wait a bit longer. Right. If we get a call from above now, next seek is 6, and base is 2. 2 plus 4, also 6. 6 not greater than 6. Therefore, we again wait here. All right. So, yep, pretty much wait here. And so this timer for the base 2 is going to tick, 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 tick. All right. Let's assume packet 4 and 5 arrive at the receiver side, which generates react of packet 1 because they are out of order. And let's just assume these two acts is just going to take a long time to come back before t for 2, the second time here, times out. Okay. What's going to happen here is that it's going to trigger the sender side, the timeout event. What do we do there? We restart timer and what? Retransmit the entire flight of packets starting from the base. So 2, 3, 4, 5 go out at once. All right. And good thing is that at the other end, the receiver here finally gets packet 2. Yeah, it's finally the expected sequence number, so it's going to call the transition on the right, extract data, pass it up, so deliver to the application layer, and therefore we generate ACK 2. And packet 3 arriving here, extract data, and then generate ACK 3, and so on and so forth.
And that's all for today. Okay, good timing. Sorry we don't have lecture time for questions, but you know what? Starting at this point, it's the office hour, so feel free to stay and type up questions if you have any. Okay. And if you have also questions about the exams, there could be errors in pollys grading, so feel free to let me know. With that said, if you have no questions or nothing you need poly for, you're free to go. Okay, I'll see you next week. Okay, bye guys. Yeah, thank you for your patience, particularly here I'll go back in, right? It's a little bit tedious and it's a little bit complicated. Okay, bye. Oh, you guys all paid attention. Thank you. All right, so I'm gonna let the video session run a little bit longer. Okay. Okay, go get lunch. Okay, bye. Ah, okay. So Catfish, maybe I turn off the YouTube live session before I pick up your call. Otherwise, our conversations will be broadcasted. So give me a second. Okay.